Hey there, my name is Jeremy Backler,
And I'm Zach Free.
and we'd like to talk a little bit about our machine learning final project, which was about audio localization on a Raspberry Pi. So our problem statement was kind of surrounding audio localization. So we wanted to focus on determining the direction of audio of an audio source, kind of like your brain and your ears do. So taking two microphones spaced a certain width apart and looking at the different signals that come into those microphones and detecting which direction that sound wave had come from based on the difference in those. So to do this, we had kind of a basic test setup. We taped these two microphones to the side of this carton. This container was about head width, which is why we picked it. And it allowed us to keep the microphones in the same spot while recording our audio for testing and for inference. And we also used a Raspberry Pi, so having an external monitor to be able to write code and run inference on the Raspberry Pi with that was super helpful.
So before we dived into the actual building a AI model, we looked at some other related works. And here were some interesting ones that really kind of set the tone, no pun intended, for our project. Echolocation was an interesting one that was fairly related. There's a couple applications, one for kind of recreating a 3D image of spatial data based on an emitted sound, and the other one was classifying behaviors in a room, standing, walking, sitting, or falling. And we were able to kind of take some of those principles and apply them to our application, which was even, I would say, simpler in theory, determining the direction that the sound is coming from. And some of the challenges that we faced, I don't think we were prepared for the challenges that we would face, but data pre-processing was really challenging because we had multiple inputs and we had to somehow combine those inputs so we could feed them into the model. And there's a lot of different decisions that we had to make around that. And we explored a lot of different options. First, just straight subtraction, just subtract this wave file from this wave file. And that didn't really give us what we were expecting, probably because the waveforms aren't perfectly lined up. How could they be? So we also looked at cross correlation. There's an example in those images there on the slide. You have your raw waveforms plotted over each other. You see they're very, very similar, but just not exact. And cross correlation is kind of a rigorous algorithm, more so than just a simple subtraction, to tell you what the similarities and differences are in the between those two signals. And that's the image is the output for that on the bottom. And then the other technique that we applied was converting it to a spectrogram, kind of like we discussed in class for audio applications. And then, of course, when you get into the actual training, there was a lot of hyperparameter tuning, and we were trying to get our model to ignore those complex features. We used our voice to create the noise for collecting data. So there was words, which are, very complex signals, but we just wanted, where is it coming from, not what is it saying? So ignore the complexities and focus on just the generic features.
So we took a couple different approaches from an architecture standpoint for some of our models. Our best resulting model was a single input RNN with LSTM layers, as shown on the left side. This gave us about a 25-26% test accuracy. And the input for this was the cross correlation data that we had from our wave files. We also implemented a CNN model, and the input for that CNN model was a spectrogram of the differential input. So taking the differential between the two wave files, turning that into its own wave file, and then making it a spectrogram. And that gave us about an 18% accuracy rate. And then the dual input RNN with LSTM layers was our worst architecture by far. We only really got 5 to 10% accuracy, which is worse than if you had just guessed out of the 9 options. So we weren't really happy with that one, but that was another approach that we had tried. And I kind of wanted to just bring it back to the kind of one of the important reasons that we decided to take this challenge on was to see if we could find a way to implement this audio localization for machines. Nowadays, we have humanoid robotics that are becoming more popular, and one of the implementations of this that might potentially be used is implementing this in a humanoid robot, so which would allow it to localize sound and be able to detect where certain sounds are coming from in real time. Um, and I think, just in conclusion, while we were unable to get results that we're super proud of, I think that we learned a lot in this project. And moving forward, one thing that we would really want to focus on is getting really good, really precise input data, and allowing the timing of that data to be strictly controlled so that we know, okay, waveform one and waveform two are being recorded at the exact same time, because that's not something that we could guarantee with our test setup, unfortunately. And our models just weren't able to um, kind of break through the uncertainty based on those timing differences. But overall, we learned a lot. We had a lot of fun, and we're pretty proud of what we were able to accomplish given some of the setbacks that we encountered. So thank you.
Thanks for watching.